Okay, let's review the Master Theorem and its application, the Master Method, and try and get a better understanding of what all the different pieces mean and how they work. So quick review, the Master Theorem applies to recurrences of the form we've been looking at, T of n equals A times T of n over B plus F of n. And it's got some specific requirements to be applicable. So it requires that A be greater than or equal to 1, B be greater than 1, and A and B must both be constants. We can't take that for granted. And n should be non-negative. So we normally think of n as being the amount of data we're processing, and negative data doesn't exactly make sense. I'm going to refer to these parameters a and b with the terms branching factor for A and the instance reduction factor for B. So I'll elaborate on those two terms in just a minute. First, I wanted to review one or two other components of this Master Theorem. So the Master Theorem has something called the critical factor, and the critical factor is an important part of determining which of the three cases of the Master Theorem we fall in. So the critical factor, C crit, is equal to log base B of A, and it's critical in the sense that it helps us identify which case we're in, but we identify that case by comparing this critical factor to some aspect of f of n. Really what we need to do is we need to assume that f of n is bounded by some polynomial in n, so some n to the power of k. And it's really this polynomial that somehow bounds n, f of n, that we're comparing against the critical factor. So I just wanted to quickly look at where this terminology comes from. So a lot of the citations of the Master Theorem refer to its presentation in this classic textbook, Introduction to Algorithms. So this is one of the most commonly used textbooks on algorithms. And in this particular text, they introduce the Master Theorem, and then they show how to solve problems, which they refer to as the Master Method, which is really just an application of this theorem. So the theorem as it's presented here is my source for the requirements on the parameters a and b in the form of the function. They use a little bit different notation than we're using. So they break the Master Theorem down into three different cases, all based on f of n, and comparing f of n to some polynomial function of n to the critical factor. So instead of writing the C crit here, they're writing log base B of A, which is the critical factor. And they subtract off an epsilon. So a couple of times I referred to things as polynomially lower. So that's what this minus epsilon is inducing. So I'm going to refer to this with the concept of less than. We'll actually focus on the idea of comparing the exponents. And if our exponent on our polynomial bounding f of n is less than our critical factor, then it's polynomially lower, and it meets this requirement of the Master Theorem. Okay, so the Master Method is just applying this theorem to solve a particular problem. So let's gain some deeper intuition about the different features involved. Particularly how A and B impact the recursion tree. So let's consider A first and think about the role of A. And again, I'm referring to A as the branching factor because it controls how many branches our recursion tree has. So we'll think about the simplest possible case when A is equal to 1. So in this case, each instance of our recursive function call may call just one other instance, which may call another instance, and so on and so forth. So we essentially get this sort of linear approach. Okay, so let's consider a little bit more interesting example. Let's consider when A is 4. In this case, our initial instance may recursively call 4 other instances, which may recursively call 4 other instances, and so on and so forth. So you can see as A increases, the overall number of branches, the overall width of the tree, and overall number of nodes in the tree also increases, and increases pretty dramatically. Now let's consider the other factor. So again, this is why I consider A to be the branching factors. A increases the number of branches on our tree and the overall width of the tree increase. So now let's consider our other factor, B. So I consider B to be the instance reduction factor. It's really the factor that's reducing the size of each successive instance of the problem. So my first example, I'm going to consider B to be 1. Now remember that for the master theorem to apply, B has to be strictly greater than 1. So the example problem that I'm showing here, we could not use the master theorem to analyze. But let's think about how B being 1 impacts the recursion tree. So here, I'm also going to think about this f of n function. I'm going to consider it to be n. So B's real role is about changing the amount of data in each successive instance. I'm also going to continue to assume that A is equal to 1, just so we have simple diagram to focus on. So our initial instance of our recursive function would process n pieces of data, and in our next instance we would divide by 1, so we'd still have n pieces of data to process, and so on and so forth. Okay, now let's move on and think about a little bit more interesting variation when B is not 1. So when it's something greater than 1, where we could actually use the master theorem. So here I'm going to try and think of something moderately large to kind of give us a high degree of contrast as we're thinking about this. So let's imagine that B is 1 million. And I'm still going to assume that my f of n function is just n. So we're going to, each instance of the function processes all pieces of data that it's given. I'm still going to assume that A is 1. Our branching factor is low to keep this kind of simple. So when our method is initially called, it has to process all the data that's given. But when it recursively calls itself, it's processing 1 millionth of the data that it was given. So the problem size in the recursive calls is dramatically smaller. And then the second layer of recursion is n over 10 to the 12th. It is dramatically reduced. And by the time we would get to the fourth iteration, we would have essentially gotten to the point where some of our largest data sizes, like a petabyte of data, would be reduced down to 1. We would almost there'd be almost no real-world instances at the moment that would actually have to go beyond 3 recursive calls or 4 recursive calls. Okay, so B is really about reducing the size of the instance, the amount of data that's passed into the recursive calls or handled in the recursive calls. Okay, so B really controls the overall height of the tree because we're dealing with discrete data. When we get down to 1 item or less than 1 item, we're essentially done. So the recursion tree is a full tree, and we've already seen that before. So we've seen full trees when we were looking at binary trees, and we did some analysis when we found out the height of a full binary tree, which is base 2, is log base 2 of n. So notice that the branching factor had an impact on the base of the logarithm. The same is true with a generic branching factor of b. If we have a full tree with a branching factor of b, the overall height of the tree is big O of log base b of the number of nodes, of the amount of data. And okay, so let's look at kind of 3 different examples, and we'll do both the recursion tree and talk a little bit about how the master theorem applies. So let's consider A and B, different values of A and B for a recursion tree and specific values of f of n. So let's consider the work at each level when A equals 2 and B equals 2. So this is kind of a special case where A equals B. And we'll look at 3 different variations of this to get a little bit better understanding of the 3 different cases of the master theorem. So first off, we'll consider when f of n is equal to some constant k. Okay, so the recursion tree will look something like this. And if you think about this, so again, the total amount of data is being reduced by 2 at each level, but the work being done at each instance has nothing to do with n. It's a constant function, nothing to do with n. Our branching factor is 2. So the total amount of work that's being done here is really that constant k times the number of nodes in the tree. Okay, so we'll come back to this in a minute, but basically this is one of our 3 cases that's handled by the 3 different cases in the Master Theorem. Now let's look at a subtle variation of this. Instead of assuming that f of n is just a constant, let's assume that f of n depends on n. And to keep it simple, I'm just going to assume that f of n is equal to n. So each of our instance calls has to iterate through all of the data that it's given for some reason. So just like before, I'm going to consider my a and b factors to both be 2. So let's draw out the recursion tree. So our initial instance of the problem has to deal with all n pieces of data, and it passes n over 2 pieces of data to each of the recursive instances, and they pass half of their data, so n over 4 total, to each of their recursive instances. One of the things you might notice about this is that the sum at each layer ends up being n. So the total amount of work that we have here is n times the number of levels in the tree. And we've already identified that the levels in this particular tree are, in general, would be log base b of n. And in this case, it'd be log base 2 of n. Okay, so let's look at a third example. So that second example is going to correspond to another case of the Master Theorem. Now let's look at the third example. Here again, I'm going to look at the same values of a and b, and I'm just going to change the particular f of n. Instead of thinking of f of n just being n, I'm going to think of it as being an n squared operation for some reason. Everything else is exactly the same. A and b are still 2. So the root of our tree is going to have to process n squared items, and then n over 2 items will be passed to each recursive case, and they will have to square that, so n squared over 4 amount of operations or work or time each. So if we sketch out this recursive tree, it looks something like this. So notice that our root does a total of n squared operations. If we look at the next level down, it's n squared over 4 plus n squared over 4. So that's n squared over 2. So the next layer down in total does less work. And the layer after that is n squared over 16 4 times. Oh, so that's n squared over 4. So it does even less work. So you can kind of see that we're getting a series going there. So we could actually formulate this as a summation, and we can find a closed form for this. But it basically ends up being big O of n squared. So we've got something somewhat unique here. Really, a lot of the work is being done at the top of the tree. So this is a little bit different than our previous 2 cases. So the work that's being done at the top of the tree kind of overwhelms the work that's being done down below. Okay, so I want to do a quick aside just to talk a little bit more about some things that are useful for understanding this critical factor. So first off, I just want to do some algebra and kind of review that sometimes it's useful to change bases in various ways. So imagine that we want to convert from log base b of n to base a. So we can use some properties of logs. We could represent log base b of n over log base b of a is equivalent to log base a of n. So this is just our standard formula for changing the base of a log. And we can rearrange that a little bit and put it in terms of log base b of n. So we can just multiply through by the denominator. So we can basically move that over there and change it into a multiplication. Okay, so once we've got this formula, let's go ahead and use that. So let's substitute that in to a to the power of log base b of n. And then we'll just do a little bit of arithmetic algebra and rearrange things a little bit. So again, I'm going to substitute this thing into this expression. So a to the log base b of n is equivalent to a to the log base b of a times log base a of n. And then I can just reorganize which of these is in which spot, commute them. So that's equivalent to a to the log base a of n times log base b of a. Okay, so once I've got that, then I can just change this a little bit, change the grouping a little bit using my laws of exponents, and say a to the log base a of n to the power of log base b of a. Okay, and then I can simplify this because logs and exponents are complementary functions, inverses. So this basically results in just n to the log base b of a. Okay, so when it's all said and done, the important part there is, starting from here, we can show that it's equivalent to that. So a to the log base b of n is equal to n to the log base b of a. Notice that log base b of a thing, our critical factor. Okay, let's get back to our recursion trees and this critical factor thing. So the critical factor is log base b of a, which we can find by taking the log of a, dividing it by the log of b. So what does it really mean? So I'm going to give kind of the abbreviated version of this. The overall height of the tree we've already identified as log base b of n. The total number of leaves, so remember the leaves are just in the bottommost part of the tree, is whatever our branching factor is to the power of our height. Okay? And we've just identified our height is log base b of n. So a to the log base b of n. Oh, we can just use that relationship that we just established, and we already know that that's equivalent to n to the log base b of a. So we're just using some kind of long-winded algebraic simplifications and substitutions here. It doesn't seem immediately intuitive because it's not, but we have established that these two things are equivalent. Okay, really the big takeaway here is that's the number of leaves, but the total number of nodes is actually bounded by a constant times that. Okay, I'm not going to go into a full derivation of that, but you can do a little bit of work and convince yourself that if you know the number of leaves, you can multiply by some constant, and it will be greater than the total number of nodes in the tree. Okay, so at this point, this n to the log base b of a, this critical factor, is somehow related to the overall total number of nodes in the tree. Okay, and that's really the big takeaway here. The critical factor, n to the critical factor, is somehow related to the overall size, the overall number of nodes in the tree. So let's go back and look at our different examples there. So we've got these kind of three categories of the Master Theorem that are represented by the examples that I've just covered. So in all three examples, a and b were the same value. They were both 2. And we looked at an example where f of n was a constant k. And we could think of that as being k times n to the 0th. So we could think of it as being bounded by some polynomial with the exponent on n of 0. So that corresponds to our case where c is less than this critical factor. So c is 0. Our critical factor is log of a over log of b. So log of 2 over log of 2 is 1. Okay, so this kind of corresponds to the case where our f of n function is small in comparison to the critical factor. The work we have is actually kind of going through and doing this entire tree. The total amount of work is proportional to the number of nodes in the tree. Okay, so work depends on the overall size of the tree, so it's theta of n to the critical factor. And remember, we've already kind of shown that n to the critical factor is essentially the total number of nodes that we have. Or it's the asymptotically the number of nodes we have. Okay, let's look at our second case. So our next case was when f of n was equal to n. which we can just think of as n to the first. So our c there is 1. So this is the case where c is equal to the critical factor. So really what this means is that our the total amount of work on each level of the tree for our specific example was essentially constant. Okay, so work depends on the tree levels and the work per node. So in this case, the Master Theorem tells us that our overall complexity is n to the critical factor. Again, that's basically the number of nodes times log n. But remember this, because this equivalence is also essentially the complexity of O of f of n. So basically this is saying that it's essentially f of n times the overall height of our tree, which is what we saw with our specific example. Okay, so let's move on and look at kind of our third case. So our third case is when f of n was n squared, so our c is 2, and that happens to be bigger than the critical factor here. So this was kind of the third case of the Master Theorem. And in this case, if you remember, our topmost node is really kind of what dominated the work. As we move down further and further down the tree, each successive layer does less and less work because the work is being reduced by more and more in this specific case. Okay, so in this case, the work is dominated at the top nodes of the tree, and our Master Theorem says that it is theta of f of n. So it's the f of n function that's really driving the overall complexity. Okay, so that is kind of the overall summary of the Master Theorem and applying it by going through using the master method.